Hello, Stuart. Good morning. How are you?
I'm good, thanks. Good morning, Antoine. Good to see you again.
So, can you present yourself, who you are, what's your company, and what business you're in?
Yeah, absolutely. So I'm Stuart Kinnear. I'm the co-founder and CEO of Interface Fluidics. Interface Fluidics is a fluid analysis and fluid compatibility company, focusing specifically on taking large-scale laboratory testing equipment and miniaturizing and adding new workflows for uh, engineers across the upstream oil and gas industry to improve the compatibility performance of their fluids.
So, what's your background? How did you come? I mean, to work for as a CEO for Interface. So,
Yeah, absolutely. So my background is I have a music degree as my undergrad, and an MBA, which doesn't really sound like the kind of pathway that leads you to running an engineering company. But after I finished my MBA, I worked at Canadian Natural Resources with um, actually in the supply chain group. And one of the projects that I worked on in my 5 years there was an RFP for all the polymer for the Britnell polymer flood. And I remember in the process of trying to understand and award that to the various proponents of that, we had a really hard time understanding not just like what product is going to be used, but why and how. And really, there was very little data that those of us in the supply chain group had access to understand the performance of these products. And so it became, a price discussion and a supply discussion rather than does the product do what it says? Well, we just have to trust the vendor. We didn't have a lot of data in that point. So that was definitely a learning opportunity for me. It was a surprise. But my co-founder, Tom DeHaas, who's our chief technology officer, was working at Suncor at the time. And he's actually the one who developed the prototypes of our technology or the early versions um, at University of Toronto. And his experience at Suncor was working in the new technology group, where his job every year was pilot one thing in the field. And he was spending $500,000 plus per test at universities trying to understand how different subsurface chemical processes would work for enhancing recovery in SAGD. And he saw them using the tech. Actually, Suncor was using the technology he had first pioneered back at U of T, waiting on data from universities. And he thought, there's got to be a better way to speed up the decision-making process and the screening process for chemistry for EOR. And that's really the genesis of Interface. And so I'm
so,
a
so
third generation
what
oil and gas guy. And so it's just natural to end up in this space to me.
what year did you start the company, and how many people now?
So we started the company in 2015. Myself and Tom went full time on the company in 2016. So it's been 10 years this year, and we now have 39 people across Canada.
That's and do you have can you share the name of some shareholders or people who invested in the company? Some
Yeah,
supporters.
absolutely. Obviously, when you start a company like this, you start with the friends and family. So our friends and family absolutely supported us in the early days, but as we grew and proved out the technology, our largest shareholder is Equinor, Norwegian state oil company, as well as Techstars, which is one of the United States' largest technology investors, most prolific technology investors. So we're in really good company and yeah, supported by really great folks that understand the technical piece of what we do.
So you're doing both, I mean, services. So you help people with their compatibility, but you are also building and supplying the equipment.
Yeah, that's right. So the basic problem we see in the world is a lack of accessibility of high pressure, high temperature, process condition fluid compatibility data. And so that doesn't logically, I think the logical conclusion is not necessarily that we should do all of the testing for all the people in the world. Obviously, we do services for folks in a lot of ways. It helped us develop our technology and prove it out, but we really want to have the biggest impact we can, which means getting our tools into the hands of engineers around the world. So that's why we provide our tools as well. And so you can either work with us on a service basis, or yeah, we do provide tools to bring in-house into universities, research labs, chemistry companies, things like that.
Can you take us through what microfluidics is, how it works, the product, the chips, and
Yeah,
the
absolutely.
tech?
I'll share my screen here really quick so your viewers can get an idea of what we're actually talking about. But microfluidics will be familiar to pretty much anybody in the world these days. It is one of the most ubiquitous technologies. It's really changed the world. If you've ever taken a COVID test or a diabetes test or a pregnancy test, these are all microfluidic devices. And really, microfluidics is just the study of fluid flow at the micro or nano scale. A lot of people don't know that those biomedical tools actually evolved out of EOR and waterflood screening tech back in the 1960s. So the first microfluidics were actually to help understand subsurface flow through porous media. Since then, biomedical industry's really taken it and changed the world with it. And Interface is one of the first companies to really bring it back into the energy space, learning all those things from the biomedical industry to do the same thing that those biomedical folks have done, which is make data readily accessible, much cheaper at the point of care, as opposed to fancy lab tests somewhere else. Makes things a lot easier. So we're recreating the porous media as well as many other portions of the upstream industry.
We have a chip. Can you show us how it looks like a porous medium,
Yeah,
even on the slide or just on the screen if you have one
absolutely.
in your
I've got
pocket?
one on my desk here. I don't go anywhere without my chips. So this is a microfluidic chip, one of our hydraulic fracturing microfluidic chips. So we recreate the nano-Darcy permeable porous media on that chip and flow reservoir fluids at reservoir conditions through it. If you want to see what that looks like a little bit bigger, the wrong slide. Just pull up an image of what this actually looks like. So what you can see there on the right is about a 1 centimeter by 1.5 centimeter silicon wafer that's had the pattern of a porous media etched into it. We then anodically bond glass on top of it, so you have an encased system. And then each little line that you see there is essentially just tubing that's baked into this process. So these are one-time use devices that most people call chips. But you might have heard them called reservoir analogs, reservoir on a chip. There's a million names for them. But this is the core of our technology. And one of the things that Interface has been able to do is build these devices and the supporting tools such that they can reach 10,000, 15,000 PSI, 200 or 400 degrees Fahrenheit, 200 degrees Celsius, 400 degrees Fahrenheit, so that we can actually use live oil representative fluids, because that's been a limitation of this technology in the past.
You were showing just before a picture about the porous medium, so how it looks. Do you have this slide to show the?
Yeah, absolutely. So I'll start with this picture here. So one of the beautiful thing about microfluidics is we're able to image using many different imaging technologies. So it helps us understand what's going on inside the porous media. So we use fluorescent imaging to leverage the natural fluorescence of the oil. We also use bright field imaging to understand, when solids might be depositing inside of a porous media. But we also use cross-polar, which allows us to see wax and other crystalline material. All that comes together into a technology we call autoanalysis, where we take a raw, in this case, fluorescent image of the chip. So this is what our microscopes see directly during imaging. We then apply a whole bunch of sort of AI and algorithm-based image processing to it to isolate where is the oil. So that's what every white pixel here. We know the volume of every pixel on the image. And so we want to know how many pixels of oil are there. We're then able to mask back in the porous media. So all the channels here that are not lit up by that oil are filled with either water or water plus chemistry. And then one of the really beautiful things about image-based analysis is we get to understand how fluids move over time. And so we can actually start to do some of this displacement process and really understand the displacement process and trapped fluids. So typically, if you're looking at a core, you're going to look at micro CT or something like that to understand fluid displacement or fluid processes over time. In our system, we have direct imaging. So every pink pixel there is oil that was trapped at the beginning of the polymer flood phase of this experiment that was then liberated by that polymer. So we can see every pink pixel is recoverable, is incremental recovery.
So how long does it take to run an experiment? So from the time you set it up till the end of the experiment, I mean, for let's take I don't know, three applications, so Waterflood, Polymer flood, and Unconventionals maybe.
Yeah, so each of those tests, we don't do anything at Interface that takes longer than a day per test. Whether you're looking at a water flood, polymer flood, or a like fracture fluid testing, those are all something we do within a day. Now there is prep time and things like that if we want to talk about um, different ways that we prepare the porous media for wettability changes, things like that. But in general, it takes us about a day to run any test that we do, if not less.
So in terms of material and structure, you can build on demand different chips, I would say, for the applications. And how far can you go in terms of porous medium complexity and characteristics?
Yeah, so what we do is we design our microfluidic chips to have the same physical structure as our customers' reservoirs. And so, as with any test or any kind of technology, there's always limitations and trade-offs. So when we start to talk about the porous media here, it's an area where it's worth starting to talk about those. Why are you working with microfluidics? Because it does become relevant here. Ultimately, microfluidics is a technology that allows us to do fluid compatibility testing or fluid performance testing in under representative but not necessarily realistic conditions. Right? This is not a real rock. This is not a real system with millions of years of history to it. And so, what we're really looking for here is to understand fluid compatibility performance under confinement that is representative, if not perfect. And so we're able to get permeabilities, porosities, in basically any range that traditional operators operate within. So nanodarcy to tens of darcy, permeabilities, porosities between 3%, 50%, pore throat sizes from 80
And
nanometers all the way up to microns.
in terms of surface charges, can you play also to make different wettabilities on the chip?
Yeah, so the chips themselves are naturally very water wet. The surface here to draw an analog or to tell you about the composition is silicon dioxide. So we've got a very good sort of sandstone or many silica-based geologies that are going to be very representative and right out of the box. As soon as we start wanting to get into sort of those more complex wet or oil wet systems, what we're able to do is actually age the chips the same way you'd age a core in a core flood. We can age our chips to have wettabilities that are representative of the system. And we've done quite a bit of work to understand how those react over time and how that changes. So there are a few papers we published with various customers of ours talking about that wettability. But I can share my screen here and just show you an example of what that actually looks like. Typically, in a core, it's very hard to get actual direct visualization of what the wettability of the system is. But because we have direct visualization of all the interfaces between any two fluids inside of a system, we can actually see those contact angles. And so by measuring the contact angle inside the porous media, we're able to actually get you, hey, is this water wet? Is this oil wet? And everything in between.
You mentioned a couple of applications also in the beginning. So in terms of, I mean, what got the most traction in your for your services? Was it conventional and historic recovery or basic? I mean, when I say basic, it's water flood and water compatibilities or unconventionals. What's today
So
the percentage of?
Yeah, the breakdown of things that we do for customers or things that customers do with our tests or with our technology is about 50 to 60% is hydraulic fracturing fluid compatibility studies, which to be reductionist about it, it's essentially a flow assurance problem where we're talking about, are we creating solids, are we creating formation damage or reservoir damage with those fluids. About 25% of our business is conventional water flood or enhanced oil recovery. And then following that, we get into more complex things like gas injection, PVT, as well as flow assurance is probably our biggest growing area right now. We're doing more and more work there.
Can you share maybe a couple of examples, so case studies for each of these? So So we understand basically the setup, the protocols,
Yeah,
results, and the benefits. Especially, if you want, you mentioned in conventional, so we can start in conventional and then go to Waterflood UR. And if there is anything about some more fancy applications, it would be also very interesting.
yeah, let's do it. So I'll start in the waterflood area. This is a paper that was actually published at the EAGE IOR conference 2 weeks ago. So this is very much a summary of that work, but we worked with a North Sea operator in their waterflood. So this was a new waterflood. It came online, and they started to see significant injectivity decline much faster than they were expecting. The suspected mechanisms here was scaling of the injection water and reservoir water being incompatible, as well as wax. This reservoir had fairly waxy crude. So they approached Interface to understand the presence of each of those mechanisms in their process, as well as the severity of each mechanism, and then to look at if chemical interventions like inhibitors would improve the performance or allow them to keep operating. So we worked with them to design a porous media based on their reservoir, which is what you see on the screen here. And then what we did is started with scaling. So what we're doing here is taking laboratory brine for the reservoir fluid and a real field sample for the injection fluid, and we're co-injecting that into this porous media here. And so what we're looking at is, I'll play a video. At wellbore temperature, which is significantly below reservoir temperature, there's very little scaling happening. And so the thing to look out for here is these little black dots. Any of these little black dots are particles of scale. And if we zoom in, we can see there's very few of them. And what you're actually measuring in this case is, because we have visual access, we can see the full pore volume coverage. So we're looking at what is the amount of the pore volume that has scale precipitated within it. On the left y-axis and on the right y-axis here is the pressure drop across the porous media. So we're going to use that later to help understand the comparisons. When we increase the temperature, so looking at deeper into the reservoir as the water heats up, we start to see significant incompatibilities crop up. So temperature really does have a massive impact on injectivity here. So significantly higher coverage. So we've gone from 0.15% pore volume coverage to almost 10 to 12% of the pore volume is covered by scale. And we have pressure drops that are significantly higher in this case. So just to compare those two, so the bottom plot here, this is reservoir condition, or sorry, wellbore temperatures. Basically, this rounds to zero damage. And then the damage factor here, which is essentially just the pressure with and without the incompatible fluid pressure drop. We have about a 4.5 times increase in pressure drop required to keep that flow going. So we see a sharp change in incompatibility at higher temperatures. So this was a good indicator for us that there is a scaling mechanism, but that scaling mechanism is likely happening deeper into the reservoir rather than at the near wellbore region. The second piece here was looking at wax. So the first thing we did was measure the wax appearance temperature using our microfluidics. I mentioned before we've got the ability to do cross-polar microscopy, which is the gold standard for wax appearance temperature measurements. But the fact that this is not a dedicated device is actually quite useful because we can just bolt this onto any test that we're doing. And so what we're plotting on the right here is the actual light intensity of the image that we're looking at and how it spikes over time. So you can see as soon as we start to see the first crystal of wax appear, we start to see those white pixels show up. So it's a very, very accurate plus or minus half a degree Celsius. So this gave us an idea of what the wax appearance temperature was in the system. Once we knew that, what we started to do was to inject the reservoir fluid at 50 degrees Celsius, so above the wax appearance temperature, and then flow that through a porous media that's being held at the near wellbore temperature. And so we can see the deposition over time. Same thing here, we're just measuring formation damage as a function of that wax. So once we confirmed both mechanisms existed and that they were both contributing, we went through and did a screening to look at 4 different scenarios where I'll play all the videos at the same time here. We're looking at recovery factor here. So the green in this case is oil and blue is the aqueous phase. And so in each case, we've either added scale inhibitor, wax inhibitor, or in the bottom right case, both, to try and understand, which of these products is going to have an impact on recovery and which one is going to, and are there synergistic effects or detrimental effects? So are they working together or not working together? So pictures are beautiful, but people are terrible at looking at pictures and understanding what's going on. And so we can start to get in and understand qualitatively, like without any chemistry, we see a whole bunch of these black aggregates within the porous media, and they become smaller and basically get eliminated with the wax inhibitor. And so likely what this is wax that's been deposited, and then the scale is actually sticking to the wax. Because as soon as we get rid of the wax or add the wax inhibitor, we have much less scale. And so together we get this really nice compounding effect. And when we plot out these the results of all these experiments, we find that the recovery factor, which is a number most reservoir engineers would be familiar with, we're getting increased performance with either one chemistry, but when combined, we get a really synergistic combined effect. So we're actually increasing recovery factor by 52% by having both of these. And then in this case, the injectivity, which is the thing that actually got, they called us for, is we see either wax or scale inhibitor dropped the injection pressure, but both together really had this massive impact on injection pressure. So overall, the outcome here was that we were able to, one, confirm the hypothesis that the producer brought to us. 2, we were able to do enough testing to really explore the possibility space. If you were to do the amount of core floods that we did on our microfluidic devices here, this would have taken years of work in core floods, and we were able to do it in just a month or so. So they got the answer they needed much faster.
I see also that the beauty, at least with the chips, is you can make the same chips. You can it's very repeatable, so you can have the same 4 chips and really compare the behaviors without scale inhibitor, etc. So it's
the ability to have repeatable porous media doesn't exist in normal core floods, right? Yeah.
So here, at least you can really, you remove the issue of repeatability and heterogeneity and
and it goes back to the point I was making before. This is not designed to be a core, right? We're never going to sit here and say you shouldn't run a core flood, right? Like that's just not the case. But one thing we do say a lot is if you run experiments where you can isolate fluid variables from rock variables, that allows you to actually understand, well, what are the contributing factors here, and really interpret both sets of results much more effectively. Because you have something that works in the microfluidics but fails in the core. Well, now you're investigating a rock fluid interaction that didn't exist in the microfluidics. So it gives engineers a big clue as to where to start looking and saves a lot of time.
So next case, you were mentioning there were unconventionals, there were EOR, also unconventionals.
So I'll see when I have a hard time understanding the specific. When people say unconventional EOR, I find it to be a little bit challenging to characterize because it means a little bit of different things to everybody. Some people that just means adding some chemistry to their frac fluids. To other people, it means going back and re-intervening in frac. And so what I will
it's probably just the formation which is unconventional. Then the rest is probably you can do the same in many cases, but just probably the rock is a bit it's unusual.
It's a bit
production
it's
engineers.
A bit weird. Yeah, and so what I'll say is when we're looking at frac fluid optimization, I think generally what I'm going to present here is used during initial completion, but pretty simple to look at what's going on in this process and start understanding how enhanced recovery comes from it. But ultimately, the big problem, whether it's water flood, conventional EOR, unconventional systems, it's all water, right? Water is the confounding factor in almost all circumstances. It's the variable we can control the least over time. And it's a thing that, especially in the unconventionals, we spend a lot of time and money on. And so we really like to focus on the water. So just to give you a walkthrough of what you're looking at here. So this chip is a bit different than the previous one. We're still creating a porous media, but this is actually a dual porosity porous media, with that triangle being a high perm, quote unquote, frac zone, with the white lines on there being the low permeability matrix, with porosity being shown in those in the pores there. So this chip is typically much less custom, because really this is a glorified filter in many ways, right? We're just looking at how different fluids block or liberate fluids from a porous media. Typically, we're in the 100 nanometer pore throat range as our standard. And so the experiment that we run here, because we're dealing with such low flow rates, we're talking single-digit nanoliters of flow per minute. We actually don't measure using traditional pumps or anything like that. When you're dealing with flow through nanoporous media like this, we use an image-based flow measurement technology. So we're actually counting pixels, and we know like I said before, we know the volume of each of these pixels, and these accumulator channels are our flow rate measurement device. So what we do here is we take oil saturated porous media, inject our frac fluid or EOR fluid of interest to displace it, start going to work. If we're looking at surfactants, we want to see wettability modification. If we're looking at other products like nanoparticles, we may want to see displacement or liberation of solids. And then we reverse the flow oil back across the porous media. And the key performance metric here is just how much oil is able to flow across the porous media over a set period of time. And then another big difference here is typically in conventional systems, you're going to run your porous media at a constant flow rate and measure pressure drop to understand your performance, which is what we do in our conventional systems. Because of the unconventional nature of this, we're actually running at constant pressure drop, which is why we need to measure flow rate. It's much easier to the amount of capillary pressure you deal with here is very significant. And so what we're going to do in this case is, we work with a company like Primex, which is now Civitas. They're looking to just screen surfactants. Are these surfactants going to be the right ones based on the water and the oil that's in my system? And they wanted to have a third-party opinion about that so they could understand what's the right thing going on. They also wanted to move away from fresh water and into produced water, which is obviously much more complex from a chemical perspective. And so we ran a very large suite of testing for them. So we did 7 different chemistries plus a brine control in 2 different water sources. So fresh water and 91,000 TDS produced water. And you can see there's error bars on all this data. So we were repeated either 2 or 3 times every data point that you've got here. So we have a lot of data. Again, this is years and years of core flooding data if you were to try and do this again. And so where they were injecting previously, the product was sample P3 over here on tap water. It's the highest performing product in tap water. But as soon as we start moving into produced water, we start seeing the sample P4 really actually outperforms everything else, even in this produced water. So this question of compatibility with the water is really continues to be paramount. And the interesting thing here is with this at a 0.5 GPT loading, or half a liter per cube, was 3 times as effective as 1.5 in the 1.5 liters per cube in the tap water. So drastic reduction in concentration combined with compatibility with the water gave us much better production. And then when we went to the field and Primex fracked those wells with that new product, the real interesting takeaways here is there was about 6% additional production at the end of 180 days, which, I'm not going to sit here and take all the credit for that. I think everybody in the world would be trying to take credit for that. And there's a lot of confounding factors. But one thing that was quite clear is we see that the peak production was actually reached about 20 days earlier. And so that's a payback of, we've halved our payback time on this well. So that was a really successful outcome. So overall, they were able to reduce their chemistry costs by about 50% on this well. Loadings were reduced by 300%, and this took about a month to do for us. So again, much faster time to decision and the ability to iterate quickly. So we do this.
In this case, it's
we're done.
surfactants and oil production. Do you have some other examples for frac fluid compatibility or with formation or something like this?
I do, yeah. So, this surfactant in water is a fairly simple system. When you start getting into more complex systems, we actually start taking into account friction reducers and other materials that might be found in there. So we work with PureChem Services up in Canada here quite a bit. They're a longtime customer of ours because I think they have a really science-based approach to their products. And so they wanted to look at how different cleanup processes like breakers impacted HVFR performance, as well as different surfactants, again, to look at cleanup processes. So everything here was all identical in terms of the chip and the base fluids and the chemistries that were being tested. The only thing that changed was the wettability, as well as the oil formation that it came from. So one was in the Montney, in a water wet Montney situation. The other was an oil wet Duvernay reservoir analog. And so we went progressively through each process, adding different chemistries to look at how much oil is produced in each situation. And we can see that adding breaker initially improved the production by about 27% in the microfluidic chip. But the longer we go, add surfactants, we have very high variability in surfactant performance. And this is something we see everywhere, whether it's conventional, unconventional. Surfactant performance is so heavily dependent on the other products that are in that fluid that, it leads us to say the most unsatisfying answer always, which is people come to us and say, well, what do you suggest? What do you see working? And we always have to say, well, it depends, which is the least satisfying answer for anybody. But we've never found a silver bullet. We've never found something that always works. It's just not a thing that exists as far as we can tell. And I know that sounds self-serving as a company that sells testing services and tools, but that's really the reason they exist, is it's very, very difficult to predict across the board. So just to summarize here what we're looking at, surfactant 2 performed very well in the water wet situation with this HVFR and breaker. When we move over into an oil wet situation, we see that this surfactant number 1 goes from basically being equal to having no surfactant at all to having 300% better performance than the baseline. Now, I will point out here, when we look at the plot of that recovery over time, one of the really interesting things to keep in mind is we are repeating a lot of these experiments. And so the variability and the repeatability of these products is very unpredictable. And while we still have a clear winner in this case, you can see that we start to see this differentiation, which is hard to get from any other test. And maybe just to summarize sort of what we've been looking at here across these case studies, there's a whole bunch of different kinds of damage mechanisms that we see that people want to understand, and microfluidics gives us this unique ability to visualize. So in many cases, we're going to have reservoirs that are super hot. You want to look at, well, what product is going to be compatible with a hot reservoir like the Eagleford? So this is work that was done for the Eagleford, where we can see chemistry company had tested their product up to 160 degrees Fahrenheit, which is, quote unquote, high temperature for most applications. The reservoir was actually 300 degrees Fahrenheit. And so this product, that when it got put in the field, started producing a whole bunch of black gunk, but wasn't replicable in the lab because they didn't have equipment that went up to high enough temperature and pressure. We start seeing that product in our chips. You look like you have a question.
And yeah, no, I was curious because typically in frac fluids, you also have 2 types of products for friction reduction and viscosifiers. Some come into powder form and some in emulsion forms. Have you had the chance to compare the the impact of both product forms on the porous medium?
We have, yeah. It doesn't matter as far as we can tell, as long as the preparation is done well. So, that's not just me saying that. I talked to quite a few people that work out in the field, and ultimately the challenge with how the product is delivered is a question of hydration and how it is the chain of custody on that product is maintained. So the question of powder or slurry or whatever you want, at the end of the day, as long as it's prepared appropriately and stored at appropriate conditions, that's going to have a much bigger impact than anything to do with whether or not it's prepared or whether and how it's started. The preparation method is key. I don't know if that aligns with your experience as well, Antoine.
Well, because for me, for instance, in emulsions, you have both the polymer and the oil. So my question was more when you have two phases, what can be the impact on the permeabilities? I mean, relative permeabilities in the porous medium, especially because we are into low perm. Yes, I know we have fractures, but if it leaks into the matrix, the question is, would there be some differential damages if you are considering the powder form, which is just the polymer in the water, or the emulsion form, which is the polymer, the oil, the surfactants, etc. So this was my question.
Okay, I think I understand better. I don't think we've tested a ton of products that are coming with as oil emulsions for loading. So typically what we're testing is aqueous exclusively. It's very rare for us to look at that. We start looking at emulsions in situ, where we start to see emulsification in some cases, but typically the emulsions are not something we're injecting.
Okay. For conventional EUR, do you have some beautiful videos and pictures to show me? I'm a polymer flood person, so if there is anything on polymer or other EUR, chemical EUR that you have, I'd be curious to see nice videos with especially the changes in sweep efficiency, even at this scale, I think.
Yeah. So the one of our favorite cases, as well as a customer that we work with a lot, is Baytex. We love them because they're skeptical, and skepticism to us is sort of the number one hallmark of people we love to work with. So they came to us wanting to understand the risk factors associated with reducing their viscosity concentrations in some of their Eastern Alberta, Western Saskatchewan heavy oil polymer floods. So they've been running Waterflood for a number of years. They bought assets. They've been under Waterflood for a decade and had started doing polymer flooding and believed that they had a hypothesis that we could reduce the concentration and all the benefits that come along with that. So we worked with them to design a reservoir analog that mimicked their reservoir. And then I say they were skeptical because there's a whole bunch of work that I'll show you here that is all published, but there's a whole bunch of pre-work that went into this that was unpublished, where we spent quite a bit of time history matching. So they said, here's our field performance, the incremental uplift that we saw with each process in a number of different fields. So we actually ran Waterflood followed by polymer flood in 3 different areas for them before we actually started doing any predictive work. So just to say, does the microfluidic chip predict future performance? And unfortunately, I can't share any of that data, but needless to say, they proceeded with the predictive work and we continue to work with them. And so that prediction really is around not the ultimate recovery factor, because everything at our scale, you're going to see a bigger recovery factor number. But the question is, what is the incremental recovery? That percent change is really what we're trying to understand and what we're able to deliver on. So in this case, you can see here the reservoir analog that we designed. Skip through that because it's probably not super interesting. But when we look at the visualizations here, so we started with just primary water flood, primary polymer flood as a baseline to see how do these look different. What can we learn from this? And I think this shows very standard, predictable sort of polymer flood versus water flood behavior. Some of the really interesting stuff, though, that if you spend enough time looking at these videos, beyond just the recovery factor numbers and the displacement front processes, but we can also see the amount of oil that's trapped in pores versus oil that is trapped as large conglomerates. You can see in the polymer flood, we actually see quite a bit of pore body trapping, as opposed to in the water flood, we start to see large ganglia that are being
And so what you these videos, so the polymer is secondary, so there was no water injection.
There was no water injection in this case. I will get to an example here,
Okay.
where we have a tertiary water flood. When we move on to the next phase, we just started looking at again secondary polymer flood, or primary polymer flood, I should say, and we're comparing viscosities. So 50 centipoise is the viscosity they were injecting at in the field, and 20 is the theorized optimal concentration that they wanted to hit. And so what we saw here is that after approximately 1 pore volume injected, we see convergence of the 20 and 50 centipoise. So really not getting anything extra out of our reservoir, but from injecting this 50 centipoise polymer. So this is what this told them is, well, you can either inject 20 centipoise for longer, and you have a lower cash flow over time, but it's also likely safe to switch over to 20 after that 1 pore volume. So there's two approaches you can look there in terms of cash flow maximization versus OPEX minimalization. And then the economics of the actual polymer start to come into account there.
It's interesting. The thing in the field, and this is a discussion, I mean, this is what you mentioned in the beginning, is the heterogeneity of their reservoir will also dictate basically the choice, because it's likely that if you inject a low viscosity, you might have early polymer breakthrough, but you might live with it. And you might get to the point you were mentioning and seeing on the graph. But if you inject 50, you might also delay polymer breakthrough in the field if it's highly heterogeneous, and you might also accelerate the recovery. So indeed, that's a very interesting threshold here that we can visualize on the graph.
Yeah, and I think it really does illustrate the points that you're making are, this is not a silver bullet. Like there's so much more analysis that needs to go into this ultimately, right? We're saying, well, from a chemistry perspective, they converge. From a cash flow and operational process and the rest of the reservoir management strategy, obviously you need a lot of tools to do that. So we see ourselves really as a screening process that can feed into the rest of those, not the be all end all.
But still, it's impressive that at this scale you still see the differences when you inject different viscosities, which is exactly the point and the goal of the study. So that's already very, very interesting.
The beauty of reservoir engineering is that everything is dominated by pore flow. And so microfluidics, we're not having to downsize anything or upscale anything. Everything is happening at the same scale that's happening in the field. There's just more of it happening in the field. And so the physics are the same. And I promised a more complex version of this. So this is the image that I actually led with here. And so what we did is water flood until we reached, I think it was 0.8 or 1 pore volume of water injected. 0.5, there we go. And then I'll pause the video here right at that initial phase of polymer injection, or final phases of water. So every green pixel here, this is oil that is essentially irrecoverable oil, right? And now that we know what those irrecoverable oil pieces are, we can actually tell the computer to go in and say, well, anytime any of those pixels are produced or mobilized, you can color those a different color. And so we start to understand, well, where is we're having additional oil production from the polymer. Where is that coming from? What is the source of that oil production? And what is it doing to the distribution of fluids within the reservoir? And so pink is actually displaced oil, and green is where the oil is after the fact. Can
you analyze the flow paths that are used by both fluids, and especially the oil mobilized during polymer flood, to see if they are, they are the same, or if it's mainly following zones where there was some oil left and going through these zones, or if it was taking, say, paths where there was mainly water and
So we don't do individual like pore mapping. Where the fluid's moving across pores. What we do is, the same way you'd look at putting pressure taps into a core in a traditional core flood, we can actually divide our porous media up into different zones or sections, and then look at recovery factor in each of those throughout the experiments. And so in this case, we can see in section 1, we see significant increase in production early on compared to the water flood. And as we get through the experiments, we actually see these. You can see the delay in where the production comes through, but we also see convergence on how much is being produced. So we see that sort of piston-like displacement here. I have one more. I'll try and pull up another image of that I think does a good job of showing that. But ultimately, these incremental production numbers here, these percent incremental productions, this is what everybody is looking for in this case. And this is what we saw was actually very, very predictive of the field within single-digit percentages when it got out into the field.
Curiosity, the test you just showed were run at in fixed injection rates, or do you have also some at fixed pressure drop?
These are all run at fixed injection rate.
And I guess you also tried some. Yeah, please continue. I wanted to ask about surfactant, polymer, and other chemical AOR stuff, but let's finish with this one.
Yeah, just to show here, this is the production plot from that field, and so what we see here is the 50 centipoise polymer injection. Here we go from about I think it's 35 cubes per day of production up to, and we see increase where they actually decreased it to 30 after a while. We saw a spike in the middle after a shut-in, but really flat production across 30, and then that flat production continues after 20 centipoise. So this was published at the Canadian Energy Technology Conference about 2 years ago. So if people want to go out and dig in, Baytex did all they put all their field data in there. There wasn't an interface publication; it was a Baytex publication.
And in these, still a couple of questions because that's also interesting. We published a paper recently about what happens when you resume water injection after polymer injection. And so is this a study you've done in a kind of heterogeneous chip, or maybe not yet?
It is not. I don't believe we've ever done water alternating polymer testing.
So because the idea would be, very curious also, but it should be heterogeneous. Like, I mean, you should have a kind of a two-layered chip with maybe high perm, low perm, but still in pressure communication, I mean. And be curious to see when you do the polymer, so you push the oil, but what happens when you switch again to water once you are done with your polymer injection. So
the closest analog we have is this work that we did. This was back during COVID. So what we actually did here is these are 4 different stacked porous media that are all in fluid communication, like you just mentioned, where we just did water flood followed by polymer flood. And so we can see here the water flood, we're plotting recovery factor by zone in water flood. And then as soon as we switch over to polymer flood, I'll speed up the process here. We get very strong, we're able to start recovering oil from, K4 here, which is the lowest permeability, lowest porosity. We're able to recover very successfully from that zone, which was basically untouchable from a water flow. So from a conformance control perspective, this is a good case study of that. And then this is I mentioned before, I had a better view of the conformance and displacement process that we do during our imaging. So you can see here, we had pretty significant fingering happen in the top porous media here, and fairly nice piston-like displacement just visually. And in this case, we're just comparing polymers that are the same viscosity, but are different molecular weights. And so we can see anytime we see production where all the lines are producing all the zones are producing at the same time with similar recovery factors, we know that that's got fairly worse conformance than in the case where if you want really nice piston-like displacement, you can have both in the same porous media. Ultimately, we ended up with similar recovery factors in the system.
would there be a way, for instance, to use the chips to compare different polymers, but I mean, with or without oil, but to characterize um, polymer retention, for instance? Is it something you've done, or?
So your typical polymer retention tests are very challenging to run on microfluidics because the pressure drops that you see are extremely small. However, Interface has developed or modified the typical. Basically, we actually adopted a test from the offshore formation damage testing, say offshore completions fluid testing industry, where they do a test they call return perm, or in hydraulic fracturing, people call it regain conductivity, where we're actually just measuring essentially formation damage as a function of injecting different fluids. So it's a simpler test than your standard MRF or polymer retention.
But even your oil recovery curve. I mean, don't know how precise things can be, but the oil recovery curve. If you have a high retention, basically, you will delay the oil bank. So it might be also a indirect way to check this. But yeah, you won't get the value. It just might be able to compare things. But let's see. That's
Yeah,
very interesting.
exactly.
And
Yeah, so like just to give your viewers here an idea of what what this test actually looks like. So in this case, we're looking at formation damage from friction reducers. So it's a three-phase experiment where you just have brine injection followed by the friction reducer. Both of those are run until you get steady state pressure drop. And then a third phase where you re-inject the brine back into that porous media that's saturated with the friction reducer. And so that's what we're plotting here is your regain conductivity percentage is the percentage of your flow. And you can see interesting, cleanup processes and different behaviors of these different friction reducers. So ultimately, see, we get really excellent repeatability here, which is typically very challenging with any other sort of natural or type of porous media.
And have you run some other conformance studies along with microgels, nanogels, or something like this in the chemical world? Or
We've tested just about every kind of wacky stuff people could throw at us.
even
Often what
tomatoes?
we get bottles labeled, polymer 1, polymer 2, polymer 3.
Yeah.
They don't tell us what it is other than SDSs, so we don't hurt people. And so, we work blind a lot, which, we don't mind that at all.
And carbonate
Leads you
reservoirs, for
to,
instance, do you have, I mean, do you have chips that can kind of mimic, dual porosity, or maybe not fractured because it's probably very difficult, but at least dual porosity, low permeability carbonates, so low perm matrix and some VUGs, for instance?
yeah. Yeah. So, I mean, we have the ability to control permeability and porosity independently in our chip design. And so you can achieve that. Obviously, this is not a carbonate system, and there's a lot going on in a carbonate system that isn't going on in our chips. However, the confinement effects and the question of wettability is still something we control. And so, it's about knowing the limitations of the tool.
For because I'm thinking carbonates, so for chemical EOR, but because there is also a lot of work with around low salinity, changing wettability, low salinity, smart water, and inhibition, counter-current inhibition, co-current inhibition. So have you run some studies already on these kind of processes, or maybe?
So we've done a lot of looking at salinity and its impact on wettability. I say we don't do nearly as much work on any in carbonates as we do in traditional sort of silicon dioxide based systems. So I would say that most of the time we're not doing carbonate work, but when we have, we're looking at the same thing you're just mentioning here, just looking at wettability modification and fluid compatibility.
Maybe some
to be honest, like people are so concerned about the carbonate as a reactive system that they often miss the basic elements of like just basic compatibility, right? Like internal consistency on the fluids is going to give you such a leg up on high performing reservoir fluids and reservoir interactions.
And
I could talk all day about that.
can you reach very high pressures to study miscible systems like CO2 injection and such?
Yeah. So we've actually, I think we've got, this is a place where we kind of like to brag, but I think our system goes up to 1,000 bar. So we're able to do miscibility studies, I think better and faster, more accurately than any other system that's on the market. Um, we developed that in partnership with Equinor, and I think over the last couple of years, we've run more miscibility studies through our lab than the rest of the industry did
Mm.
combined, because it takes us 15 minutes to run the equivalent of a 2-month slim tube experiment. Um, and so we collect orders of magnitude more data more quickly.
Did you
Yeah, we've
use
done a lot of cool stuff there.
some wax studies maybe already with CO2?
Yeah, we're in the process of working with a couple of folks. We actually haven't done too many WAG studies internally, but a lot of our customers that have purchased Sapphire Lab and brought it into their facilities are doing WAG. So
Okay.
we're working with them to do WAG studies. So we've got universities in Brazil and Thailand both running WAG studies, and uh, we're looking to have at least one more unit out doing WAG by the end of the year here in the US as well.
Is there maybe any other case studies you'd like to share something you like very much or something we didn't discuss yet?
I think I mean, I could go through case studies all day. One of the things that we had discussed going through is just, where is this going to go? Beyond the reservoir, because I think um, the longer we've been around, the more of a holistic view of fluids and fluid compatibility has started to creep into our minds at Interface. And when we think about the future, um, so the reservoir performance is obviously critical, but those fluids then make their way up into the process. And it's very challenging today to do anything like near real-time fluid compatibility, or understanding the impact on our production systems is typically very challenging. And so where we see our technology going and is the ability to look at flow assurance and surface processes as well as the subsurface gives us the ability to, will give us the ability to close the data loop between what do we think is going to happen, which is really what we've talked about today, is predictive testing, right? How is XYZ product going to behave once it gets into my system? Let's be as representative as possible. But I think without understanding what's happening in the field and looking at what's coming back and how is it impacting our production processes, is it what we thought it was going to be? We're missing a lot of data. We're missing a lot of information, and I think we're going to see oil companies that adopt real-time monitoring or near real-time monitoring of fluid properties and fluid interactions in the field have a significant advantage. And so that's where we see this technology going as well.
So do you think so? What do you think it's gonna encompass? Would you have to make something that you can take to the field, something portable, for instance, a smaller device, or something that you can plug in, and run easily anywhere in every
Yeah.
part of the world?
Yeah, ideally that, Sapphire Lab, our tool was designed from the beginning with the idea that it'll go to the field eventually. So as it is, the tool itself, you can put it anywhere that's got 4 walls and a roof. It is not an inline monitor yet. As we go further down, we'll understand, the workflows that are going to emerge from this. But we're expecting to have our first field implementation of Sapphire Lab, not just like a laboratory base, but like out in the lab, in the field, doing near real-time fluid analysis, either later this year or early next, to
And
look at the
any
production
others?
processes and the subsurface.
And so, any other exciting, I would say, development? So you mentioned unconventional, conventionals, water floods, and then moving to flow insurance. What's
Yeah.
is maybe what would be? Is there any other next step in addition to having something that people can use, like even like their phone in the field, and to check what's happening in almost real time, because it might not be real
Yeah,
time.
that's definitely the vision. One of my favorite, when we think about where this industry is going, I actually think that over the long term, there are far more processes in the world than just oil and gas processes that are happening in the subsurface involving production of resources. So we worked with a company called Summit Nanotech here in Calgary, who is a direct lithium extraction company. And when I start to think about, like you said, what are we looking at in the field? lithium extraction is this really complex brine chemical process where you've got a lot of risk because you're producing high salinity brines. You're then doing a bunch of chemistry and modifying those processes, and then trying to re-inject those brines back into the reservoir they came from. So you have just a bunch of places where you have potential issues. And so we did some work last year, published it at EAGE as well, on brine injection, which is obviously a thing that the oil and gas industry is very familiar with. But as we get into these non-hydrocarbon energy sources like lithium, geothermal, hydrogen, CCS, these are all water problems, right? They exhibit the same scaling issues, the same formation damage issues that the oil and gas industry is experienced with, but they don't have the same, I would say, demand for their product or the same commercial structure, and so it's much harder. They're much less resilient to this kind of operational interruptions, and so being able to predict what's going to happen and then take Sapphire Lab, put it in the field to monitor, like, how is your compatibility changing over time, being able to react to that very, very quickly is of utmost importance in the future. Whether that's oil and gas or non-hydrocarbon, I see water compatibility and water management for formation damage mitigation as one of the number one topics that I think the industry is going to be talking about over the next decade.
And so for you as
so we want to be positioned well to provide that solution and be able to mitigate that risk as fast as possible.
And so for you as Stuart, as an entrepreneur, so it's interesting because you mentioned that you don't have I would say you worked in the oil and gas, but not in the chemistry or microfluidics background. So what advice can you give to people who have an idea and say, okay, that's maybe I don't have all the knowledge, but I might just find my peer or duo and let's start something. So what have you learned and things you can share as an entrepreneur that you think some entrepreneurs in becoming would be happy to hear?
Yeah, I mean, I think the most important thing for me is that, yeah, I don't have the background, but I'm super curious and I love what we're talking about. I find it to be endlessly fascinating. And so I don't find it difficult to go, I would say the first 7 years of the company, I was reading technical papers every day, trying to just understand better what's going on. So I'd say I don't have a degree in it, but I went to the University of Hard Knocks in the real world. So I think I've educated myself. You're never going to hear me tell anybody I'm an expert, but I think I know enough that I understand the fundamentals. And I think that's really important. It's like, what I would say to anybody is you don't have to have a degree in what you want to do as long as you really give a shit. And if you really want to do it and you think you really care about it, I think anybody can do anything like this. But you have to surround yourself with really smart people and really take the time to be humble and ask questions. That's what I would say. But other than that, you just go for it. No time like the present.
Few moments you're very, very proud of since you started Interface?
Yeah, I mean, there's so many, but I'd say one of the proudest moments was when we started working with Equinor, really building that relationship over time. But they came to us and said, like, if we could have minimum miscibility pressure data, we love that data, but we hate every method that actually generates that data because it's all the reasons that people do that. The fact when after 9 months of R&D, we had developed a method and measured the MMP of 3 different fluids as accurately or more accurately than the lab that they had hired to compete against us without our knowledge. So we developed the method and made the measurements faster than they were able to make the 3 measurements. And coming out of that with the method being that excellent and having gone on to be the most used way to measure that technology, but that fluid interaction is something we're super proud of at the company. And I think gave us a lot of motivation to keep going.
So you have
shows the versatility of the tool.
You have the proud moments, and that's a very, very nice one. And maybe something you would do differently now if you you had to start again. So what would be the stuff that say, okay, now I learned the point, and I'll do something. I'll do it very differently now.
Yeah, this is one of those ones where I would do a million things differently, knowing what I know now. But I'm not sure I would know those things without making the mistakes. And so it's such a hard trade-off. I think we spent a lot of time uh, doing things that would never scale or that didn't solve a problem at scale that maybe one person cared a lot about and was willing to pay for, but ultimately was never going to be something that could, be a company. And so I think knowing what I know now, I would not have spent a year developing a diffusion coefficient measurement. Yeah, it's the best diffusion coefficient measurement in the world, I think, but nobody cares.
Might prove useful at some point. Who knows?
I think there's places where that might prove useful, and I think it'll come back around one day. But that I think that attitude of like build things if someone's willing to pay probably held us back. But I think we could have been more aggressive over the years too. Like I think we could have gotten into the I think we look a lot down at startups that happen in the US where they move a lot faster than we have. Then I think we could have moved a lot faster over the years, but we're still here 10 years later, and that's a low probability thing, all statistics in. So I'll take it as a win.
Thanks, Stuart. Any maybe a few things I missed or you wanted to share about the company, and how to reach you? Probably LinkedIn is the easiest way, and with the website.
Yeah,
Will
my
you
LinkedIn
be at
is,
the conference soon somewhere? So if people are interested.
I hope so. We're just wrapping up some sort of reservoir engineering processes here at the company. So I'm hoping to get back on the road really soon. See people at ERTEC and ATCE, as well as some of the EHEE conferences later this year, maybe even ADIPEC. But that's probably what you'll definitely run into folks from my team at almost every major SPE or EHEE conference this year. So definitely come say hi. Excuse me. But yeah, if you reach me on LinkedIn, my phone number and my email are both right on my LinkedIn. So just text me. I'm super easy to get a hold of, and I love chatting with folks. But if you want to reach out, info@interfacefluidics.com will go to me, goes directly to my inbox as well. So would
Well,
love to chat with any of the listeners.
thank you very, very much for taking the time. And once again, if I will be looking for the new publications and papers, especially in the chemical EOR world, and I think there will be more. There will be different problems coming soon because what you've published is mainly on sandstones. That's why I mentioned carbonates, because that's probably the big deal now, especially Middle East. So I look forward to seeing what's going to happen in the next 3, 4, 5 years, and maybe having a portable device in the field to do some fast, I would say, compatibility studies. So, well, thanks again, Stuart, for your time. And,
yeah, thank you very much, Antoine.
Thank
It's
you,
great
Stuart.
chatting with you.
Bye-bye. Thank you.